Welcome to Unit 4, which is on estimation and hypothesis testing. Section 7.1 specifically is on estimating a population proportion. Now, in order for us to estimate, any of the parameters, we need a point estimate. And a point estimate is a single value used to estimate a population parameter. And for the population proportion, we are going to be using the sample proportion, p hat, to be the best point estimate of that population proportion p. P hat is an unbiased estimator of p since it targets that population proportion p when constructing a sampling distribution where the mean is p. So we would have, p in the middle here, denoting when we have our z-score equal to 0, that type of thing. It is also consistent since the standard deviation of the sample proportions tends to be smaller than the standard deviation of other unbiased estimators of p. But we won't be looking at those, just p hat. So for example, if the touch therapists had the ability to sense a human energy field, they should have identified the correct hand significantly more than 50% of the time. If they made random guesses, their success rate should be around 50%. Using the result of 123 correct responses in the 280 trials, find the best point estimate of the proportion of correct responses. So p hat, we're going to take that 123 correct responses, divided by 280 trials. Toss that into a calculator, you get about 0.439, rounded to 3 decimal points, of course. The best point estimate for the percentage of correct responses is 0.439. For the confidence intervals, which we can also refer to as interval estimates, the range or interval of values used to estimate a true value of a population parameter, and it could be abbreviated as CI for confidence interval. The probability 1 minus alpha, alpha being significance level, such as 0.95 or 95%, that the confidence interval contains the population parameter, assuming the estimation process is repeated many times. It can also be called the degree of confidence or confidence coefficient, and we typically could have confidence levels of 90, 95, or 99%, and the corresponding value of alpha, again significance level, of 0.10, 0.05, and 0.01. And interpreting a confidence interval, we are blank percent, that would be 1 minus alpha, so basically the confidence level. We are blank percent confident that the interval from the lower bound to the upper bound contains the true value of the population proportion p. We could describe what that population proportion means in English words here at the end, but since this is a general way of writing it, that's why it's written as such. This tells us that the process that we are using should, in the long run, result in confidence interval limits that contain the true population proportion 1 minus alpha percent of the time. And in the picture down here, we could see that this is supposed to be a 95% confidence interval, and most of these intervals contain the value of p of 0.5, except for one down here in green. For the critical values, this is when certain requirements are met. The sampling distribution of sample proportions can be approximated by a normal distribution. And a z-score associated with a sample proportion has the probability of alpha divided by 2, so the significance divided by 2, or half of the significance, of falling in the right tail. As you can imagine, the left tail is the same probability of alpha divided by 2. If you add these two tails, you get alpha, which is why we divide by 2. The z-score at the boundary of the right tail region is denoted by z sub alpha divided by 2, and is referred to as a critical value because it is on the borderline separating z-scores that are significantly high. But in order for us to calculate this critical value, since this is typically written as the probability that z is greater than some number x is equal to alpha divided by 2, SAS, and for that matter most technology, gives you the error to the left. So that's the same thing as the probability that z is less than x is equal to 1 minus alpha over 2. So for a 90% confidence level, alpha is 0.10, alpha over 2 is 0.05, and the critical value is 1.645. For a confidence level of 95%, alpha is 0.05, critical value, the alpha divided by 2 is 0.025, and the critical value is 1.96. For 99% confidence level, alpha is 0.01, alpha divided by 2 is 0.005, and the critical value is 2.575. For example of calculating that critical value, we just saw it on the last screen, but if you want to do a 95% confidence level, alpha is 0.05, alpha over 2 is 0.025. Our 95% confidence are between the positive and negative versions of the z-score, but the area in both tails adds up to be 5%. Area in the rightmost tail would be 0.025, and so the area less than the positive z-score will be 1 minus alpha divided by 2. So 1 minus 0.025 makes 0.975. So the probability that z-score is less than that value is equal to 0.975. And if you check SAS for that, you get a value of 1.96. The margin of error occurs when we are using data from a simple random sample to estimate the population proportion p. The difference from the sample proportion p hat is indeed an error. The maximum likely amount of that error is the margin of error e, and there is a 1 minus alpha probability that the difference between p hat and p is e or less, and it's also called the maximum error of the estimate. That calculation is z sub alpha divided by 2 times the square root of p hat times q hat divided by n, and q hat is just 1 minus p hat. Nothing too special about that. The confidence interval for this, for estimating the population proportion, we require a simple random sample, a fixed number of independent trials for 2 categories of outcomes whose associated probabilities remain constant, and that is useful for the binomial experiment, which is what we need in order for us to do this, and that there are at least 5 successes and 5 failures to use the normal distribution. The confidence interval takes p hat and subtracts and adds the error, and we can add, display that in different ways. But now we want to round the confidence interval limits to 3 significant digits. So to actually compute the confidence interval, we verify the requirements and assumptions, calculate the critical value of z sub alpha divided by 2 for the desired confidence level, evaluate the margin of error as z sub alpha divided by 2 times the square root of p hat times q hat over n, and then calculate the confidence interval limits p hat minus e and p hat plus e, rounded to 3 significant digits, and then of course write the conclusion based on that. So, for example, let us examine an experiment with touch therapists where they made correct responses in 123 of the 280 trials. The sample results are n is equal to 280 and p hat is 123 over 280, which is 0.439. We first need to check those assumptions, so we have a simple random sample for this. The n is 280, and those are independent trials. We have 2 potential options of correct versus incorrect, and the probability of being correct on here is 0.439, and it's fixed. So it's a binomial experiment. The number of successes is 123, number of failure is 157, so it's normally distributed. For the margin of error, E corresponds to the 95% confidence level. Taking 1.96 times the square root of 0.439 times 0.561 divided by 280, we get a value of about 0.0581. For the 95% confidence interval, then, we took the p-hat value of 0.439 and added and subtracted 0.0581 for the margin of error to get 0.381 and 0.497 for the lower and upper bounds. But since we want to know if we can safely conclude that the touch therapists had a success rate equivalent to tossing a coin, both of these are less than a half, so that's a no. For the point estimate, we could calculate it if we already have the confidence interval by adding the bounds, lower and upper bounds, and dividing by 2. For the margin of error, we could subtract upper bound minus lower bound divided by 2. For my next example, the article High Dose Nicotine Patch Therapy by Dale Hurt et al. In the Journal of the American Medical Association, volume 274, number 17, includes this statement. Of the 71 subjects, 70% were abstinent from smoking at 8 weeks. 95% confidence interval, CI, 58% to 81%. Use the statement to find the point estimate p-hat and the margin of error, E, where the confidence interval is 0.58 is less than p, which is less than 0.81. We add those two, 0.81 plus 0.58 divided by 2, to get 0.695 for p-hat. And the margin of error will be 0.81 minus 0.58 divided by 2. That's 0.115. We could use these confidence intervals for hypothesis tests, which will be based on if the interval contains the population proportion. But as you could assume, since it's talking about an interval, it's not as nice of a usage as the p-value will be later in this unit, but it's still a good measurement. The requirement for finding the required sample size. This is the sample must be a simple random sample of independent sample units. When an estimate of p-hat is known, we take z sub alpha divided by 2 squared times b-hat times q-hat divided by the margin of error squared. If there is no known estimate of p-hat, that will be z sub alpha divided by 2 squared times 0.25 divided by the margin of error squared. This is 0.25 because we are assuming that p-hat and q-hat are the same number, which is 0.5. And then we always round up to the next whole number as needed. So, for example, if we were to conduct a survey to determine the percentage of children older than 1 year who have received measles vaccinations, how many children must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? Assuming that a recent study showed that 90% of children have received measles vaccinations, well, we take 1.96 squared times 0.9 times 0.1 divided by 0.03 squared, with 0.9 being p-hat and q is 1 minus 0.9, so 0.1. Toss that into a calculator, you get 384.26. Rounding up, we get 385. So we had 384.26. We round that up to 385. Assuming that we have no prior information suggesting a possible value of the population proportion, we take 1.96 squared times 0.25 divided by 0.03 squared. You get 1067.11. That rounds up to be 1068. The disadvantage to this confidence interval, which is referred to as a WALD confidence interval, that's just the name given to it. This is coverage probability, the actual probability of such confidence intervals that contain the true population proportion. We typically have the confidence level of fewer. Some better confidence intervals are the +4 method, adds 2 successes and 2 failures. Then the WALD confidence interval is calculated. It has better coverage probability since it's closer to the confidence level. The Wilson score is a coverage probability is closer to the confidence level, and it's a different type of confidence interval. And the Klopper-Pearson method. It's an exact binomial distribution calculation, but it's too conservative and complex. The coverage probability is greater than or equal to the confidence level. Thank you.